Hi, we are going to talk about how to do a CAD design and then import it into FEniCS, because of course until now we have done everything by using this rectangle mesh or box mesh, which is already defined in FEniCS, but it's particularly difficult if you want to have a more sophisticated geometry, which is nowadays possible by using like softwares, SolidWorks or CATIA or whatever you like Fusion or so. So I'm going to show you a program which is called Salome. Salome is open source, of course. You can download and start using it in all operating systems. So it is particularly useful and really in the direction between SolidWorks and CATIA. So there is here a modulus, you can have different stuff, like shaper is a possibility where you can have parametric studies. You can have parameters and change these parameters, and your geometry or topology is changing automatically. There's a geometry module, which is simply like doing a CAD design. It looks like SolidWorks. And there's a mesh where we are going to put a mesh on it, which is necessary for the finite element method later on. And even the paraview is inside, so you don't have to have an additional paraview. You can also use Salome, and inside Salome you can visualize the results. There are also a lot of other stuff which we are not going to use, but it's technically something which is allowing to write Python scripts and do additional these kind of modules and so on. This is why people like to use it. So we're gonna go to geometry directly, and one nice stuff that you can do in Salome is actually you can produce directly three-dimensional. Of course, you can also do a sketch and then use extrude or revolve or whatever you want, but it's also possible to do directly simple stuff by using three-dimensional geometries like a box or like a cylinder. Let me produce a box, for example. I always think like I'm using millimeters. Okay, so I'm using here in the coordinate system x and y. For example, we can have like 10 centimeters, so 100 millimeter. And let's think like in the z direction we have, I don't know, maybe something thin like 5 millimeters. So I can see apply and close means like closing this window. I can do apply and then this window will be open, so I can create another one as well. So what I'm doing is, for example, let me say apply and close. Now I can construct another stuff which is going to be a cylinder, and the height is not important because I'm going to delete this part. So I'm gonna make a round circle stamped plate. Okay, so the height is not important. Let me put like 10, and then the radius is important, which is like, is this too small? Okay, let's get this one. So I'm getting the cylinder. See on the left hand side there's a 3 here, so we have a box and cylinder. Of course you can just get rid of it so you don't see it if you just press on the I. And this cylinder, so I'm using my mouse in order to make it bigger. Of course you can use also here like different frontal and backward vision, and also you can use like this in order to rotate it and so on. Okay, now I'm going to multiply this cylinder, or just do a copy of this cylinder. For this you have different transformation. You can of course do a translation or a rotation, or you can have a multi-translation, which is particularly useful if you want to have like many holes, for example. So we can have a multi-translation in both directions, right, in x and y. So the vector u is actually already have been selected correctly. I think I can also do it like this, so but it's already correct. So v is done. Now I'm on the tree. I have the y-axis, so I'm really saying on x and y-axis I want to have 3 times, for example, or I want to have 5 times, and also in the other direction maybe only 3 times, and the step in between them maybe 15 is not a bad idea. So that looks good. So I'm gonna take this. I can also change in one direction a different step size in between, and I will say apply and close. I have a lot of small cylinders, so I'm gonna use this box, and I'm going to transform by using a translation. So I'm gonna put it like on x and y in such a way that these cylinders will be stamped out of it. So I'm doing like an X, I don't know, let's put it -5. Is it enough? I think I need more than that, so maybe -10. And on the Y I'm doing like -30. Okay, that looks okay. So apply and close. As you see, it's making always like a copy of it, so you don't have to do it, but if you have copies, sometimes it's good. If you want to delete it, you can immediately delete it. So now I'm going to use the translation. This is the translated plate, and I'm going to cut from this cylinder the multi-translations. So this is the main object, that's the cylinder, and the tool which is like cutting out is the multi-translation, which is just the name. You can change the name as well. So if I say that, it's technically cutting it. So that's the geometry. It's a nice geometry, like a plate with holes, you can say. Okay, so that's going to be our geometry. So if you want, for example, you can even like fill it in again with the multi-translation, right? So if you want to fill it in, then you need to choose both of them and then make one partition out of it. So you can also make a partition, two objects are together. So this is also possible. So if you want to have this kind of a geometry, for example, you want to have a steel plate and inside you have like a thermoset plastic filled in this kind of stuff, and then you can have like two different materials and two different domains, right? So you can have that. So for the moment I'm going to use this one, so I'm going to have only one material, not two different materials, and I'm going to mesh this geometry. Okay, so now I'm changing to the module which is called mesh. So the cut geometry, this is what I'm going to use. I'm creating a mesh on it, so that's here, but you can also find it on top, the same stuff as a list. So I'm creating a mesh on this cut, and the type of mesh that I'm going to use is tetrahedral. So there are lots of different possibilities. One of the simplest methods, which I like, is the NetGen algorithm. This is also an open source algorithm which is working pretty well, done in Germany, in Aachen. And this is 1, 2, 3D is like starting with one dimension. The lines will be like putting nodes on it. 2-dimensional will be triangles, and 3-dimensional the tetrahedron. So you can have default hypothesis, which will be like coarse elements, or you can have also some parameters or simple parameters. Let's go to the parameters. This is technically they're saying the maximum size. Let's put like maximum size 6 and the minimum size 1. Okay, so if I say this, then there's only the information there, but it is not done yet. So I need to go and then say with the right click, compute. So compute means like compute the mesh. Okay, so it's not like a computation that we do as a finite element. It's a computation of the mesh regarding the hypothesis, regarding the function that I'm using there for the maximum and minimum size. The number of nodes is like only 1600. It's relatively coarse mesh, if you like. So of course I can turn it and you can see how it looks like. Okay, so now let us use this relatively coarse mesh, and we want to make a finite element simulation on this. So we need to have the Dirichlet boundary condition and Neumann boundary condition. By the way, it looks a little bit weird because of the way of showing it. That's orthogonal mode. If you like to have more perspective mode, which is more like nice to show it, then you can also use, of course, this one. Okay, there's only visualization problem that it doesn't look like really symmetric. So now we can go back to geometry and say, look, I want to have some surfaces like clamped, and one surface like loading is put on it. So in order to do this, I'm going to go to this cut geometry, go make a right click and create groups. Okay, so one group will be the domain, the 3-dimensional. I mean, I have only one single material, so it doesn't mean a lot, but still I'm going to do it. Okay, I'm selecting it and then adding it. There's a number which I don't care, so I'm just giving a name of it. So I'm gonna say continuum body. just a name that I needed later on. So I'm going to say apply such that this windows is there. If I say apply and close, the windows goes up. And now I'm going to select surfaces. So for example, one surface, let's make it a bit fancy. Let's think like we are holding it here, okay? So I'm selecting one, that was this one, okay? And I can also select the other one. If you say, oh, it's difficult to select it, of course you can also select something else and hide it. It's easy to select internal stuff. So select this one and hide it. You know, you can just hide it. It's not deleting, it's just hiding from the visualization in order to make it like easier to select this surface, for example. Okay, so now I have two surfaces selected, and I'm gonna give a name, for example, clamping. Okay, so I'm clamping in two surfaces there. So if you want to see it, what we have selected, then on cut, if you open it, then you see here body and clamp. So you can just visualize the clamp. Also get rid of the cut itself. So this is why, because we have scenes, I have to close it and to get rid of it. So you see now we see these two surfaces are the clamp surfaces, and that's the whole geometry. So I need to create another group which is for the loading. So for example, let me put a loading, I don't know, maybe on this surface, okay, and add. Okay, that's the surface. I can select also many surfaces, but I'm just saying, searching. I mean, it depends on the engineering problem that you have. So I'm gonna say apply and close. So we have three different domains, if you like. And now I need to say that these domains are going to be used in the mesh. So this is why I'm using here and saying create groups from geometry. And it maybe automatically come here if you do first the geometry and then the meshing, then it will be already here. But because I did first the meshing, then later on the geometry, then I need to select them using shift and selecting all of them. You see it here. And then I can say apply or apply and close. If I say apply, then it's applied, then I need to close it. Okay, that's only for the window to close. So here we have groups of volumes and groups of faces that we have. So I can also again visualize what we have here, and that's the whole body. So now we're done. I need to export it. I'm exporting here with, again, right click, export as a MED file. So MED file is just a type of file that we are going to use it to convert to the FEniCS algorithm. You don't need to change anything here. It will automatically export all necessary fields. And there are also like backward compatibility, but we can use the newest one. Okay, so now I'm doing it. I just exported. Now we have done successfully exported the MED file from Salome. So now we need to convert it to something that FEniCS can handle with that. There are different options, but one particular good option is actually an H5 file, which is particularly interesting if you want to do parallel computation. If you will not, this is a really effective method of doing it. So in order to do that, we are going to use the Docker version, right? So we have this Docker. So it is depending on your operating system. You need to start the Docker. So I'm starting it by using here connecting or mounting the present working directory, which is this pwd, to the home FEniCS shared directory. Okay, so I'm doing it. If you never did it before, then of course you will just need to download it will automatically download the Docker image for you, and after that you are going to be in the same directory as your own directory where you have started this. So there are a few things if you never did it before, so you need to do an update and upgrade. So it's always like doing an upgrade. An update is like first you need to do an update such that it takes the list of additional or recent developments and so on, and then you need to upgrade as well. And I'm gonna do it, but it will not do anything for me because I did it just before that. Okay, so and if you do it, then if you close the container, for example, I'm closing now the Docker container, starting again, so everything is lost. So that's actually on purpose done so you can test anything you want. You cannot break the system, so you can just close the container, open again from the same image, and the image is not changing, only you change the container. But if you want to change the container itself, so before exiting you need to commit changes. Okay, so there's a Docker commit, and for this you need to know the container ID, and actually you see the container ID right here. Okay, so if you then use a Docker commit by using this container ID, then all the changes that you did will be written to the image. So then next time if you start the image, there is a local image in your computer, so it downloads and you have the local image of the Docker. So after committing it, then you can start again another container from the same image another day after you close this container. Then you will just continue where you end up. So that means if you do an installation of a new program, and so it is good to commit it. And then, so you also need to have a Gmesh. Gmesh is a program which is converting this MED file to something which we call Gmesh file. It's also an open source program, and you can do it by simply downloading it from the latest version from the internet. Okay, so it is actually here. So if I put it, sorry, if I try to copy this specific information, I will also put it so you will find it. So you can get wget is like you are trying to get a file, so you just get this file from internet, and it's the latest stable version of Gmesh that you can get, and then it will also save it to your local directory. So let me show you. I already did that, so that's my local directory in the shared one. So we mounted to the shared one. So in the local directory I already have the Gmesh 4.8.4 version. So this is necessary in order to start something which is this file. Is it? So not this one. Which is this file. So this is the conversion file. So this is converting it. In the beginning of that, you see there is the link to the Gmesh. The rest you don't need to know or understand. It simply goes to your MED file, Gmesh file, and reads line by line, and then changing the nodes and elements and so on, and write it in a format, in a binary format that FEniCS is understanding. And later on, after we did the conversion, we will use this converted file in FEniCS. Okay, let me show you how to do the conversion. So we're gonna make it like this. There's a program which is this MED file to H5. What's the name of it? And there's one server edition. So where is it? So I'm gonna use the server. A conversion, not server edition, conversion, and then I need to put the name of the MED file. I just export it, and then it's asking me keep temporary files. So there's a bunch of temporary files. So it's converting by using the Gmesh to an MSH file, which is converted to XML file, and XML is converted to H5. You can have a look in that. They are all ASCII files, so you can open and have a look. But technically speaking, you don't need that. There's the default setting, which is written here capital, is no. So if I enter, then it is like deleting after using all of them, then deleting the unnecessary files. The only file that is then you can find is technically the H5. Okay, so that's the file we need, and that's the file which includes everything. There's an additional information here, but you can also find the same information in a txt file, in a text file. It's an ASCII file which has the same name as the mesh file. So MED had the name mesh_1. You can of course give a better name than that. And this has also a txt file which you can open and have a look at what it looks like. So you can either open directly on terminal, it has exactly the same information, Or if you don't like this kind of stuff, then you can also, of course, open it here. Okay, so by the way, that's the txt file, so you can have the same information here as well. Okay, so let me go back to the code. So the code is only actually changing the beginning. Okay, so in the beginning I'm putting, instead of using a box mesh or rectangle mesh or whatever it is, now I'm using something else. Now I'm using the mesh_1 because this is the name of the h5 file. Okay, instead of writing directly here, so I'm writing like data and then using it here because I mean, this is a little bit easier to do it here. But of course, I can, instead of that, do like this. So I can write immediately into it. Okay, but that there is no difference between them. So now I'm reading this hdf5 file, which is the type of the file, and here I'm also giving the MPI communication, because if you want to run parallelly, that this information is important. The dimension is 3, so I'm going to use it, and there's cells mesh and faces mesh. The cells mesh is not so important here because technically speaking we have only one and the same material. But if you have like different materials, then the cells mesh will be important as well. And the facets mesh has all the information, and also here the information has been summed up. I just put it in. Okay, so this is not necessary. It's normally not that I just put it in because from here I just copied it. This is a terminal, by the way. You cannot simply copy it, but you can use Control Shift and C. Okay, not Control C, but Control Shift and C. Or you can also use a right mouse click depending on the terminal that you use. You can also copy it. But this information is technically giving us the dimension, which is 3-dimensional for the body, and for the surfaces that we have chosen 2-dimensional, and also an ID. So this is the marking. If we have been marking with numbers 1 or 5, these numbers are here. So it has simply chosen in any way. We don't know how it is choosing, but it's 1, 2, 3 as you see. So I want to use these numbers 2 and 3. So because of that, I can directly use 2 and 3. That's okay. Or I can produce a list. So this is technically a Python list, and Python dictionary, not a list. It's a Python dictionary. So the dictionary, a dictionary has always like 2 values. So one is like the key, it's clamp, and the second one is the value of this. That's here too. So I'm producing here a dictionary because later on I'm gonna use the dictionary IDs by using like clamp from the IDs. So is it necessary? No, I can also write here immediately 2. Okay, that's technically simply 2. Why is it 2? Because this is the boundary condition, which I use the name clamp, and on this boundary condition, which has just the number 2, I want to apply something. Okay, so I can use it like this. It's a little bit easier to read it, and later on, if I use a different geometry or I change something in Salome and these numbers have been changed, for example, so I don't need to change everywhere in the code, search for it where it is, so I can just change the dictionary. So it's a little bit more tidied up, but it's just syntax sugar, so it's not really necessary. Now we can have here the boundary condition, which is the Dirichlet boundary condition, but on top of that we can also have the Neumann boundary condition, which is here. So now I'm not doing any marking anymore because all the marking has been done already, and now I'm using the num for this marking, and the rest of the code is the same. So I'm constructing a linear variational problem and then solving it. Okay, so let me see how it looks like. So if I run this, so by the way, I always have to run sudo. Sudo means like super user do. So why I'm doing it? Because there are like problems with Docker. So if I show you, like here, you see, if I show you the directory, whatever it is, so there's like FEniCS, which is the Docker container itself, but then there's root. This is whenever I use sudo, it is creating root, and these are the files. Just a funny number, 1001 is a user. These are the files that I am mounting with my local system. So because of all these mismatch, so most of the time I have to use sudo. normally speaking, it's not a good practice, but because we have a Docker container, I don't care. So if if the Docker container is like doing something wrong, I just delete it and download again. So there's nothing like to lose by using the Docker container. That's the nice stuff of having an isolated system. So now I want to start the code, which is elastostatics. Now it is like constructing all the stuff and then going to solve it. So it has been solved, and it's after solving it, it is writing a displacement pvd file, so which I can see it on a paraview. So the Salome has a paraview as well, but it's not the latest version, so it's a little bit an older version, maybe not working very well. So it's always easier or better to use the latest version, which you can just simply download. It's an open source working also in all operating systems. So because we are mounting, like in Docker, I'm doing the calculation, but actually it's writing to my local directory. So now I'm going to my local directory, which is here. And in the local directory, you see there's a pvd file. So technically it's just an information. The real stuff is in it. So you can also open this one, doesn't matter. So apply, and now we have here the solution. So I'm searching, getting here the solution. So as you can see, I have a really nicely written here UI in millimeter magnitude. So why this is happening? Because I have written here a function and given a name. So whatever name you want to give, you can have it here, and then in paraview it will be automatically shown. So, and you can also use text, like you can really use like mathematical stuff between a $sign. So I may have like, okay, this is the one. So and this is like the magnitude of it. So of course I can change it if I don't like what is written here. So here I can change the stuff that is written, so I don't like the magnitude. And also, I mean, you want to have maybe a bit bigger, I don't know, maybe 25 or 30. Yeah, it looks a little bit better. And also it doesn't really look nice with these different style of writing it, so I'm not gonna use an automatic labeling. Instead of that, I'm gonna use like maybe 3F or maybe 2F, I don't know. So this is like float with 3 digits. Okay, there's too much of this, so I can have like maybe 2. And this is E is the engineering, like with this E 10 to the 0, 10 to the power 0. It's also a little bit unnecessary. I want to use the same formatting. Okay, the first number is like how many before the dot, and the dot 2 is like how many digits after dot. So, and this looks good. So I can of course stretch it, make it nicer. It automatically puts a bit more numbers, maybe something like this is looking good. And I can also change the color coding. So this is like here, you can have some preset nice ones. These are the default ones. If you say no, I want to have more, then you can also show all. So there are a lot of more. Okay, so you can choose whether you want. And then of course we can see in 3 dimensions. So it's really difficult to understand what's going on. Because of that, I want to deform, so it's warping by vector. I'm putting the displacement on top of the coordinates. So if I just put once, then you see the deformation is really small. So we barely see something, but there's actually happening something. In order to show that, I'm increasing the scale factor. And then if I show it 50 times, then you realize that this was holding, right, clamping here, and we were putting, I think, these two some forces. Because of that, it is getting deformed. There is a relatively coarse mesh, of course. I can show you here the mesh, right? But it's pretty okay. At least it's fast. So if you want to have a finer mesh in Salome, you can use a finer mesh. And remember, we have chosen like the maximum element length and the minimum element length. You can play with them and have a finer mesh, export it, convert it by using this MET to H5 file, and then you can run the same code again. But don't forget, in the code always to check if these numbers are changing. They may change at the moment of conversion. So technically that's it. We did simple geometry which can be as complicated as your imagination, and we converted by using the markings, or we have chosen some groups in the geometry, and by using this marking method we can simply calculate whatever you also want to calculate only by using open source programs. Thank you.